Section: Introduction. In this section, we introduce long-context large language models, LLMs, which have significantly improved our ability to handle various tasks that involve large amounts of text, such as summarizing documents, analyzing legal texts, assisting with coding, and engaging in conversations. During the decoding phase of transformer-based LLMs, the key value cache, KV cache, becomes a bottleneck because its size increases with both the length of the text and the number of inputs. For instance, the Llama 3.1-70B instruct model requires about 320 gigabytes of KV cache storage when processing a batch of 32 with a context length of 32,000 tokens, which is challenging for even the best hardware. Research has shown that we only need a small number of KV tokens at each decoding step to maintain accuracy. If we can predict these tokens in advance, we can switch from dense to sparse attention operations, leading to significant improvements in memory usage. We categorize these methods into two types: permanent KV token eviction, which saves both memory and storage but risks losing accuracy if important tokens are discarded too soon, and dynamic KV token selection, which keeps all tokens in memory but may require additional storage for extra data. To balance memory efficiency, capacity, and model accuracy, we propose RocketKV, a two-stage method for compressing the KV cache. In the first stage, we introduce SnapKV++ for coarse-grained permanent KV token eviction, enhancing the previous SnapKV method with adaptive pooling and full compatibility with grouped query attention. In the second stage, RocketKV employs a hybrid attention mechanism for fine-grained dynamic KV token selection, estimating which tokens to keep based on their importance. By combining these two stages, RocketKV achieves significant savings in memory and storage while maintaining accuracy across various models and tasks. Our contributions include identifying the limitations of existing methods, proposing RocketKV with its two-stage approach, and conducting thorough evaluations that show RocketKV can match the accuracy of full KV attention while using as few as 256 tokens. We tested RocketKV on an NVIDIA H100 GPU, achieving up to 3 times faster performance and reducing memory usage by up to 31% during decoding compared to using the full KV cache. In the related work section, we note that many recent strategies aim to enhance the efficiency of attention mechanisms in LLMs, especially for long contexts. Some methods involve sharing KV caches across layers or selectively dropping attention in certain layers. Others use mixed attention designs, where some layers apply global attention while others use local attention. Techniques like multi-query attention and grouped query attention reduce the KV cache by sharing it among multiple attention heads, but these require changes to the attention architecture from the start. We also see training-free techniques that improve attention efficiency, categorized into those that accelerate the prefill phase, the decode phase, or both. For example, streaming LLM combines different types of attention to keep the KV cache size constant regardless of the input length. Other methods, like duo attention and razor attention, enhance this by applying different attention styles to different heads. Some approaches focus solely on the decode phase, such as permanent KV cache eviction, which can reduce bandwidth and storage needs. Techniques like SnapKV and Quest aim to identify and retain critical KV tokens while minimizing accuracy loss. However, many of these methods do not address KV cache storage issues. InfiniGen tackles this by moving the KV cache to CPU memory and fetching only necessary tokens to the GPU. MagicPig finds that using importance sampling is more efficient than top K selection. In contrast to these prior works, RocketKV uniquely combines both permanent KV cache eviction and dynamic KV token selection, achieving significant memory and storage savings without complex system-level optimizations, while still maintaining high accuracy even with low token budgets. Section Summary. In this section, we introduce RocketKV, a two-stage KV cache compression method that enhances the efficiency of long-context LLM inference by combining permanent KV token eviction with dynamic KV token selection, achieving significant memory savings and speed improvements with minimal accuracy loss. We also review related approaches that aim to optimize attention mechanisms in LLMs, highlighting how RocketKV uniquely integrates these strategies to maintain performance while reducing resource demands. Section: Proposed Method, RocketKV. In this section, we propose our method called RocketKV. We begin by observing that existing training free key value, KV, cache eviction methods for speeding up the decode phase can be divided into two categories: permanent KV cache eviction and dynamic KV token selection. To evaluate the effectiveness of these strategies, we compare the accuracy of 4 different methods using the Casper benchmark on the Mistral 7B Instruct V0.2 model. The methods Duo Attention and Snap KV fall under permanent eviction, while Quest and Spark are examples of dynamic selection. Our findings show that the accuracy of all methods declines significantly when the token budget is below 1024. We also introduce Exact Top K as a reference method that performs sparse attention on the top K KV tokens based on exact attention scores. Exact Top K maintains high accuracy even with a token budget of 256, highlighting that practical methods struggle to accurately predict top K KV tokens at lower budgets. To enhance prediction accuracy, we note that permanent KV cache eviction and dynamic KV token selection can complement each other effectively. We can first apply permanent eviction with a larger token budget and then perform dynamic selection on the remaining tokens. This approach minimizes the risk of losing important KV tokens and reduces the complexity of dynamic selection since it only needs to focus on a smaller subset of tokens. Based on this observation, we introduce RocketKV, a 2-stage KV cache compression method aimed at accelerating the decode phase. In the first stage, we implement coarse-grain KV cache eviction to eliminate less important tokens while retaining most of the significant ones. The second stage involves fine-grained dynamic KV token selection on the remaining tokens, followed by top K sparse attention. We divide the compression ratio evenly between the two stages, ensuring each stage achieves a compression ratio of the square root of the total ratio. For the first stage, we present Snap KV++ as an efficient KV cache compression method. Snap KV++ improves upon the original Snap KV by being fully compatible with GQA and using an adaptive kernel size for pooling. Instead of keeping KV tokens based on individual attention heads, Snap KV++ aggregates attention scores across groups, reducing redundancy. It also employs pooling to select critical KV tokens along with their neighbors, enhancing accuracy. We find that larger kernel sizes are optimal for longer input sequences, and we implement a simple mechanism to adjust kernel sizes based on sequence length. In the second stage, we propose a hybrid attention method that utilizes sparsity in both the head and sequence dimensions to improve the accuracy of top K attention score estimations. Our hybrid attention algorithm consists of 3 steps. First, we group tokens in the key tensor and store their minimum and maximum values for efficient access. Next, for each query, we identify the largest indices and fetch the corresponding values from the auxiliary storage. Finally, we perform sparse attention by retrieving the full key and value vectors based on the top K indices. By splitting the compression ratio evenly between the 2 steps, we avoid significant accuracy loss from overcompression. Our method is also compatible with GQA, as selections are made based on attention groups rather than individual heads, similar to our enhancements in Snap KV++. Section Summary. In this section, we propose RocketKV, a 2-stage KV cache compression method that combines permanent KV cache eviction and dynamic KV token selection to enhance prediction accuracy during the decode phase. Our approach utilizes Snap KV++ for coarse-grain eviction and a hybrid attention mechanism for fine-grain selection, effectively reducing the risk of losing important KV tokens while maintaining high performance. Section: Cost Analysis and Comparison. In this section, we analyze the costs and compare different methods. We note that the decode phase of large language model inference is mainly limited by memory, meaning the time spent in the attention module is closely linked to the total memory traffic. We introduce a token budget, denoted as T, to estimate the memory traffic for each attention operation during decoding, focusing primarily on the key value cache traffic, which is the largest contributor to memory usage in this context. For instance, a token budget of 512 indicates that each attention module must retrieve a total of 512 key and value pairs from memory. For models using group query attention, GQA, this token budget applies to the entire attention group rather than individual heads. We define the total compression ratio, C, as the sequence length, S, divided by the token budget, T. In our RocketKV approach, we split this compression ratio evenly across two stages, with each stage having a compression ratio of the square root of C. Consequently, in the first stage, SnapKV++ leads to reductions in both KV cache storage and traffic by this square root factor. In the second stage, we must account for the extra memory storage needed due to approximation attention. We further divide the square root of C into a quarter power between the two steps in our hybrid attention algorithm, resulting in a memory overhead of 2 divided by the cube root of C. Thus, the total KV cache storage and traffic in RocketKV are 1 divided by the square root of C plus 2 divided by the cube root of C, and 1 divided by C of the full KV baseline, respectively. We compare the KV cache storage and traffic of RocketKV with other methods at a specific compression ratio, C, and observe that while all methods save on KV cache traffic, only RocketKV and SnapKV also reduce KV cache storage, whereas Quest and Spark require additional storage for auxiliary data. Regarding system-level optimizations, RocketKV works seamlessly with flash attention since it does not alter the attention mechanism during the prefill phase, and it is also compatible with tensor parallelism, as all operations are uniform across attention heads and groups. For our experiments, we utilize 3 popular long context models: Llama 3.1-8b Instruct, Mistral 7b Instruct v0.2, and LONGCHAT 7b v1.5 to 32K, which we refer to as Llama 3.1-8b INS, Mistral 7b INS v0.2, and LONGCHAT 7b v1.5 throughout the paper. The first 2 models are based on GQA, while the last one uses multi-head attention, MHA. We assess various downstream tasks using benchmarks like long bench, needle in a haystack, and ruler, comparing RocketKV against several other methods, including full KV, exact top K, duo attention, SnapKV, Quest, and Spark. Exact top K serves as a reference for sparse attention with precise top K KV token selection. We evaluate all methods across different KV token budgets per attention group, except for full KV. RocketKV, Quest, and Spark incur extra memory traffic for top K approximation, which we convert into an equivalent KV token budget to accurately reflect the total memory loads in the attention module. More details on our experimental setup can be found in the appendix. In our accuracy evaluation, we vary the token budget from 256 to 4096 for each method, excluding full KV, and compare the average accuracy across all tasks for each benchmark. Detailed results with accuracy breakdowns for individual tasks are also available in the appendix. For the long bench benchmark, we present the average score comparison of RocketKV with other methods across all 3 models. Our findings show that RocketKV consistently outperforms the other methods, particularly at lower token budgets. For Llama 3.1-8b INS, RocketKV experiences almost no accuracy loss with a token budget of 512 and above, and only a 1.1% drop with a budget of 256. RocketKV shows slightly higher accuracy losses for Mistral 7b INS v0.2 and LONGCHAT 7b v1.5, likely because Llama 3.1-8b INS is better trained, making it more resilient to sparse attention methods, a trend also seen with exact top K. Spark performs well on Llama 3.1-8b INS and LONGCHAT 7b v1.5 with a token budget of 1024 and above but underperforms on Mistral 7b INS v0.2. SnapKV achieves decent accuracy with a token budget of 1024 and above across all models but cannot reduce the token budget to 512 or below for tasks in long bench with a maximum of 512 generated tokens, as it only compresses the KV cache of the input prompt, not the generated tokens. Although we cannot display the average accuracy score of SnapKV for those cases, the accuracy scores for the remaining tasks are available in the appendix, showing a widening accuracy gap between SnapKV and RocketKV. For the needle in a haystack benchmark, RocketKV achieves accuracy close to full KV across all models, even with a token budget of 512, and shows negligible accuracy loss with a budget of 256. In contrast, other methods experience significant accuracy drops, with SnapKV showing over a 20% decrease in accuracy for Mistral 7B INS v0.2 and LONGCHAT 7B v1.5 compared to full KV, even at a token budget of 1024. We provide heat maps of RocketKV under various token budgets in the appendix. For the ruler benchmark, we evaluate all methods across 3 models with different sequence lengths. Again, RocketKV demonstrates strong performance and a clear advantage over other methods across various token budgets and sequence lengths. Overall, we observe that the accuracy loss of RocketKV is minimal for short sequence lengths and gradually increases with longer lengths, likely because these models are less robust to sparse attention in longer contexts. The accuracy gaps between RocketKV and other methods widen further with longer sequence lengths. Section Summary. In this section, we analyze the memory traffic and storage efficiency of RocketKV during the decode phase of LLM inference, highlighting its advantages over other methods in terms of KV cache storage and traffic reduction, particularly under varying token budgets. Our experimental results demonstrate that RocketKV consistently outperforms competing methods in accuracy across multiple benchmarks, especially at lower token budgets, while maintaining compatibility with existing system optimizations. Section: Efficiency Results. In this section, we present our efficiency results from experiments conducted using Llama 3.1-8B INS with FP16 precision on an NVIDIA H100 GPU, utilizing a batch size of 1. We employed GPT-Fast, a low-latency Python native LLM framework, for our efficiency tests. We discovered that a Python implementation of RocketKV within GPT-Fast effectively showcases its efficiency, although it could be enhanced with custom CUDA kernels and advanced frameworks like Flash Infer. Our findings, illustrated in the figure, show the speedups and peak memory savings of RocketKV with different token budgets during the decoding phase, all normalized to full KV. The peak memory usage includes allocations for waits, activations, KV cache, and other metadata. We observed that RocketKV achieves up to 2.9 times and 3 times speedups with token budgets of 512 and 256, along with peak memory savings of 30% and 31.4%, respectively. Additionally, we noted that increasing sequence lengths leads to nearly linear improvements in both speed and memory savings. In our ablation study, we further validate RocketKV's effectiveness, with more results available in the appendix. We found that SnapKV with the Grouped Query Attention (GQA) enhancement consistently outperforms the original SnapKV, particularly with low token budgets. This improvement arises because GQA allows compressed KV tokens to be shared across the entire attention group, making it more efficient than storing them separately in each attention head. However, GQA does not affect LONGCHAT7B v1.5, which uses multi-head attention. We also conducted extensive experiments to assess the impact of kernel sizes for pooling on RocketKV's accuracy, focusing on the ruler benchmark. For Llama 3.1-8B INS, a kernel size of 63 is optimal for sequence lengths of 16K and 32K, while a size of 511 is best for 64K and 96K. We set the switching threshold to 48K, the midpoint between 32K and 64K. For Mistral 7B INS v0.2, a kernel size of 63 is optimal across all sequence lengths, eliminating the need for switching. For LONGCHAT7BV 1.5, a size of 63 is best for 8K and 511 for longer lengths, leading us to set the switching threshold at 12K. We found that our adaptive kernel selection, based on empirically determined sizes and thresholds, generalizes well across other benchmarks, so we did not pursue more complex solutions. Finally, we compared the accuracy of the standalone hybrid attention mechanism against Quest and Spark. Our results, shown in the figures, indicate that hybrid attention consistently outperforms both Quest and Spark, especially at low token budgets. This highlights the benefits of hybrid attention, which effectively utilizes approximations in both head and sequence dimensions, unlike the single-dimension methods used by Quest and Spark.